All right, welcome back to our exploration on functions, where we will be spending some time combing through graphical representations of them and identifying their features and attributes. Today, we're going to be learning to identify the features of a graphical representation of a function, so I can describe in writing and orally how the features correlate to a situation in context. I'll know I've got it when I can identify the characteristics of functions based on their graphical representation. We have some new vocabulary words today, so make sure that you define those. And let's begin. Many properties of a function are more easily obtained from a graph than from the rule that describes the function. To analyze the graph of a function, we must keep in mind that the height of the graph is the value of the function. And by height, we mean the output or the y-coordinate. So one of the topics we've been harping on the past week or two has been domain and range. So I'd like for you to share with your classmates how to use the graph of a function to determine its domain and range. And then algebraically, what is the domain and range of this square root function that has been provided here? I'm sure we'll have to recap this tomorrow, but it has been something we've been going over quite regularly. So moving on, when we have the graph of two functions, the solutions to the equation f of x equals g of x are the values of x when where the graphs of f and g intersect, right? So intersection graphically means algebraic equality, for lack of a better, for poor mechanics. Whereas the solutions to the inequality f of x is less than g of x are the values of x where the graph of g is higher than the graph of f. This is the bread and butter of mathematics, when we're able to tether an algebraic understanding to its graphical representation. So I would like for you to compare and contrast the solution path to solving an equation to how do we look at it graphically, right? And this is what we've just typed in this box, and vice versa with an inequality. What are some similarities? What are some differences aside from the apparent? One is a picture, the other one looks like standard mathematical notation. Here, as you can see, we have the graph of 2x squared plus 3 and the graph of 5x plus 6. I am not going to name either one of them. That is your responsibility. But you are tasked with determining the values of x by which these equations and inequalities hold true. If I were able to zoom in and click here, I would have to make an assumption. If this is negative 10, 2, 4, 6, 8, this would be roughly, I'm going to say, x equals z negative 0.75. And the other value I would have to say is roughly 3-ish. I'm sure if I was able to, I can select these points. Who would have known? 3 works, the output is 21 for both, and negative 0.5. So you can click the graph. Okay. So at negative 0.5, the output for both functions is 3.5, and at 3, the output for both functions is 21. I could have also obviously solved this algebraically, but that is not the point here. The point is to determine these values graphically. So Determine what this inequality is saying and the subsequent x values that satisfy those inequalities before moving on to increasing and decreasing functions. Right? We say that a function f is said to be increasing when the values of the graph are rising. Right? The behavior of the graph is rising and is said to be decreasing when the behavior of the graph is falling, as we can see here in our image that was provided. The way to really think about increasing and decreasing behavior of functions is to think about a roller coaster. Your intuition kind of informs you whether or not the roller coaster is going upwards or falling downwards. Make sure that when you're looking at a function, though, we're looking at it from left to right and kind of mirroring this experience that you've had if you've gone to a theme park. So according to the definition of increasing and decreasing functions, f is increasing on an interval I if, now we got some mathematical notation, f of x1 less than f of x2, right? If the second point is greater than the previous point, then we can say whatever x sub 1 less than x sub 2 and I, right? So if we have 2 points in succession, right, let's take a and b, all right, and we see that f of a is less than f of b, then we can say that the function is increasing. And then obviously if we write the ladder where the first coordinate is greater than the second coordinate, still with the first coordinate coming before the second, we would say that the function coincidentally, whoop, what just happened? All my work is gone. Go figure. But coincidentally, we could say that the function is falling. Some words of wisdom from the definition, we see that a function increases or decreases on an interval. Your location, right, which can be defined or thought of as a single point, cannot um, infer increasing or decreasing behavior. It's constant, stagnant, it's a point. When things are increasing or decreasing, that's over a period of space or a period of time. So checkpoint 3, we've provided you with a function f, and you're tasked with identifying the following. What is f of 2? What is f of negative 2? The domain, the range, the intervals upon which f is increasing. I will identify 1 at the point 0. We can see, and I can drag my point and see that the outputs are increasing up until, what is this point here? 2. Right, so I know that the interval, one of the intervals that the function is increasing along is 1 to 2. I can see that from negative 1 to 0, the function is decreasing. And the reason why I'm using parentheses is because none of those points can be included in the interval of increasing or decreasing because they are defined instances where there is no increasing or decreasing behavior. And then identifying any local maxima and local minima. If these words sound foreign, then you're going to have to return to this slide, to both those slides, after you get your definitions from here, right? Our local extrema. So maximum and minimum values occur when we have instances where a function value, so f of a, is greater than or equal to all of the function values when x is near a. In this case, we say that f has a local maximum at x equals a. And when a particular function value is less than or equal to the function, we say that f has a local minimum at x equals a. More or less, we're looking for these curves within a function that occur once we start working with quadratics and cubics and anything that has a degree of 2 or higher. Sometimes functions have multiple maximum, multiple minimum, sometimes they have one, sometimes they have none. But once again, we're looking within an interval. In our final checkpoint, we have a function here that represents the number of cars that are safely traveling a particular highway at a given speed. She finds that the number n of cars that can pass a given point per minute is modeled by this function with x representing speed. What is the maximum carrying capacity of the road, and at what speed is it achieved? There are some key context clues there. Make sure that you are attending precision in writing your response, and that will bring us to our enhancement opportunities, to which we will sharpen, and hone our skills together in class.